section, we're going to talk about a lot of vocabulary. We have a new equation for you, and that equation is simply y equals ab to the x power. And we have a couple stipulations, and they mean different things for different parts of the equation. Here we have a is greater than 0. We notice that's going to be the same thing either way, and this is the same equation. And the first thing we're going to do is talk about growth, and the growth really comes in when we look at the b value. B has to be greater than 1. Greater than 1. This means that we're going to talk about growth. So as soon as I look at an equation, the first thing I do is I look at the base. And if that is greater than 1, it is a growth factor. And when we look at that, it's now we're out of linear items. So it's not going to be a straight line. We're going to get a curve of some sort. Some of them be a lot steeper than others, and some of them won't be. So if b is greater than 1. So a couple different things that we highlighted, some connections we want to make. So in your notes, you want to make sure you're drawing something to put these things together. Now, if the b value is less than 1 and it's still greater than 0, now we're talking about decay. So again, I want to make some sort of connection. So when I look at that b value, we're talking about a decay, and we'll see it coming from the left side coming down to the right, left to right going down. So almost like a negative line. So that's the whole thing, is reading the base, the b value. So if it's greater than 1, it's growth. If it's less than 1, but greater than 0, it's decay. So when they ask the first question, which of these numbers could be growth? Well, 85% is actually 0.85. Well, 0.85 is less than 1, so that is not a growth. So 3 is definitely greater than 1. 1/2 is not. 1.05 is greater than 1, and 0.93 is not. So they're going to ask the same question in reverse. So which ones could be decay this time? Well, now I'm looking for things that are less than 1. So I know 3 is out. 85% is 0.85. So that's a good one. 1/2 is less than 1. 1.05, I can stop right there when they have something after the point. And then 0.93, that is less. So that is going to be a decay factor. So if this was in the equation as the b value, then that would make these true for growth and true for decay. So now I want to be able to use this to model some exponential growth. So suppose the population of a town, let's say it was York, was 25,000 people in the year 2000. If the population grows at 1.5% each year, what will the approximate population be in 2025? Well, we have a couple things already. So our initial value is going to be A. So 25,000, that's what we started with. Or initial value or current in this point. So it is currently 25,000 people. From 2000 to 2025, this is the years. New population, so this is going to be my answer then. And this whole thing here, the b value, and we know it's going to grow at 1.5% each year. Remember, if I want to change 1.5% into a decimal, I'm going 2 places left. So that is 0.015. And to show that it's a growth, what we do is we put a 1 in front of it. So this is the growth rate. And if I do my calculation, 1.015 to the 25th power times 25,000, we're going to get 36,273 people. So that's how we can use it to model. So I have years, I have the growth or decay rate. In this question it was about growing, so growth rate. And I start with the current value or the initial value. Alright, let's try that again. So since 2005, the amount of money spent at restaurants in the United States has increased at 7% each year. So increased, so B is 7%. So that's going to be 0.07. And then since we're talking about a growth, I'm going to use 1.07. In 2005, about 360 billion was spent at restaurants. If the trend continues, how much will be spent in restaurants in 2015. So X, the number of years, is going to be 10. A is 360. We'll give our answer in billions. That way we don't have to use huge equations. So we have y equals 360 times 1.07 to the 10th power. So we're going to do 1.07 to the 10th power. Take that answer times 360. And with our calculator, we'll find 708.17. And our answer should be in billion dollars. Okay, so if we can get everything set up, modeled, that's what we want right now. And everything after that is calculator. 1.07, we use the caret button on calculator to the 10th power. Take that answer times 360. So that gives us a couple of growths. Alright, so let's check our got it now. Let's work backwards. The kilopascal is a unit of measure for atmospheric pressure. Probably learning about this in science class. For atmospheric pressure at sea level is about 101 kilopascals. For every 100 meters increase in altitude, the pressure decreases 11, so it decreases 11.5%. So what is the pressure at an altitude of 5,000 meters? So 5,000 meters. So if we take everything and let's go by thousands here. So let's use 5 for x. Our initial value, so initial value at sea level is 101. So A is 101. And B I want a decrease of 11.5%. Alright, so we're going to use x is 5, A is 101, and for B, I want a decrease of 11.5%. And if I use 0.115, this is going to tell me how much we have lost instead of how much we have left. So I want to use 100 minus 11.5, right? Because percent is out of 100. So I'm looking at 88.5. And then I want to use 0.885 because this is all percents on the left-hand side. So if I use this value for B, it will tell me exactly what the pressure is instead of having to do an additional calculation. And that's the trick. With all of our decreases, we're going to end up using 11.5 or 100 minus 11.5. Okay, so that's gonna be how we get that. So let's plug everything. Y equals A is 101. We have 0.885, which it says decrease. This number is less than 1, so that's a good thing. To the 5th power. All right, we're going to go from 1,000 meters to 5,000 meters. The change is 5 there. Let's plug everything in. And we should end up with Y equals 54.8 kilopascals. Right, so that's how our decreases work. So they're just going to be a little bit backwards, but we'll get the hang of it. Business purchases a computer system for $2,000. Tax code allows them to take off a portion for that purchase for each year the computer system is used. If the value of the system depreciates, right, that means it goes down 15% a year. So right now I know B is depreciate 15%. And so if you lost 15% on a test, what would you have? Okay, we have 85%. So that means I want to use 0.85. That's B already. The A value, how much was the computer system worth? $2,000. And the last part, how much is the computer worth after 4 years? So 4 years is going to be our X. So Y equals $2,000 times 0.85 and to the 4th power. So according to this calculation, your $2,000 computer is now worth $1,044 and a penny. Alright, using these formulas, a big thing that we use our exponential for is based on compound interest. So the formula below gives the balance A, so we're going to set it equal to A. So the balance, this is going to be what we end up with in an account that earns compound interest. This is all for compound interest. The formula is an exponential function, so that's why we start dealing with it. So you talk about real life example, here you go. With an initial amount of P, so that's the principal, that's how much you have put in, that's the amount of money you put in. And the growth factor is going to be 1 plus R over N to the nth power. And in this case, we're also going to take it times the number of years, T. So 1 plus R, so that is the annual interest rate as a decimal, right? We've already started doing that anyway as a decimal. So if it was 5%, we're going to use 0.05 as a decimal, time in years, and number of compounding periods per year. And so if they say annually, that's 1. If they say quarterly, right, there's 4 quarters, so 4. So we'll deal with that as we get into the word problem. So the first thing is just trying to get the calculations done. Okay, so this is our interest rate of 4.5%, and it's done 12 times a year. So all we're going to do here is practice some calculations. So all we have to do is 0.45 divided by 12, add 1, take that to the 12th power, and times 1200. Okay, so I'm going to jot some answers in here, but I need you to grab a calculator from someplace and work these out, or first thing in class tomorrow, use your calculator and make sure you get these values. Okay? 53887. You also notice that they're all rounded off to the penny, because now we're going to talk about money for this stuff. When we talk about money, we always have to stop at the penny. We don't have money that's less than a penny that any of us understand anyway. Alright, so let's get this whole thing together. So our actual balance is going to be equal to the principal times 1 plus the rate over the number of times of years to the number of times of years for the number of years. Suppose your friend was born. Okay. I'll suppose that when your friend was born. Okay, great. Your friend's parents deposited $2,000 in an account. Okay, so that's the principal. That's what we started with. 1 plus an account paying 4.5%. 4.5%. Remember, we're going to move the decimal 2 places. 0.045. 0.045. Interest compounded monthly. So if it's compounded monthly, there's 12 months. So that means monthly, monthly. And they're going to do this for 18 years. So that means 12 times 18 as the exponent. So we have a couple things we want to take care of. Make this, so 12 times 18, I don't want to do that calculation twice. That's 216. And we just have to work on our calculator skills again when we come in and get the final answer. So 0.045 divided by 12 plus 1, take all of that to the 216th power and then times 2,000. And what you'll find is that even though that money just sat there, since it compounded monthly, it is now turned into the $2,000 turned into $4,489.01. No lie, it was 1 cent on this one again. So rundown, we had the principal was 2,000. The rate we have above 0.045. The number of times per year is 12 because it said monthly. And the time in years is 18 years. So that's how we end up plugging everything in. Alright, so let's see what happens if it's done quarterly. Okay, so we're going to take 18 years is our time. Quarterly turns n to 4. And we're going to keep everything else in the problem the same. Let's see what type of difference we get. So remember, the amount we're going to get was $2,000 times 1 plus 0.045 all over 4 this time, times quarterly times 18. So one thing I like to do right away is just cross this out, make that 72. So whatever that product is, I want to get that right away. And we're going to find out that now the amount is up to $4,475.53. It doesn't seem like a big deal, but compounding monthly instead of quarterly has gained us, what, $10, $14? $13.50. Now this is money that you didn't have to do anything for. So if you can get it compounded more often, that's going to raise you more money in an investment. But that's how we do it. Alright, so a couple of review items here. So what is the growth factor of the equation? Well, this is A and this is B, so it must be 4. What is the initial value of the function? Well, if this is the growth or decay factor, and that's the exponent, then this must be the initial amount. What is the decay factor? Well, 17 is the A value, so 0.2, and it is a decay factor. A population of fish in a lake decreases 6% annually. What is the decay factor? Well, we have a couple items working here. We know B is a decrease of 6%, but the decay factor, right, if you lose 6%, you have 94%, so 0.94. Some books will interchange these, that sort of thing. I'll take either, because I understand that you understand what you're doing. So you can tell me decrease 6%. Remember, 6% is 0.06. And what you're actually going to use in the equation, so that's why I think this is the most important one, is 0.94. Suppose your friend's parents invested $20,000 in an account paying 5% interest compounded annually. So that means n equals 1. We have an A value of $20,000. Of course, here's our rate. And did that for 10 years. So I'm going to get you set up. I want you to calculate this when you come in. Or if you have a calculator in front of you, go ahead and do it. 5%, 0.05 all over 1. And this is 1 time a year for 10 years. So we can get a calculation here. How can you tell if an exponential function models growth or decay? Remember, y equals ab to the x power. So make sure you can answer this question. Is it a, is it b, is it x? Which part tells me growth or decay, and how do I know? So if you're not sure, go back to the very beginning here. How can you simplify the compound interest formula when the interest is compounded annually? Explain. I'm not worried about this tonight. Okay, don't worry about this one. We'll take a look at that as we get through it. And then error analysis. Let's find out what happened here. $500 principal earns 3.5%. There's the rate, compounded quarterly, so that means 4. So n is 4. That's not a problem. And the year or the time is 2. Yeah, I think I see what it is. Hopefully you've already identified it. And here's what it is, but what should that 3.5 be? So make sure you can take care of these two. Okay, so when a calculation and 6 and 8, you can do all of this, then you're doing pretty doggone good, and we'll work on the rest of this in class.